everybody, it's Ajanette, and I'm here to do your Chapter 3 lecture. And so I am just going to go ahead and share my screen. Okay, so here we are on Chapter 3. And Chapter 3 is going to start your measures of central tendency. Again, I'm going to go back to the fact that we have two different types of statistics. Descriptive statistics, which are used to describe our data, and we use descriptive statistics to kind of simplify and organize our data. And we've already learned about frequency tables and distributions and how that helps to give just a good overall view of our data set. Now we're going to learn about measures of central tendency. Measures of central tendency are in fact descriptive statistics, and in general they tell us how similar our data points are. And so we're going to talk about three measures of central tendency in this chapter. We're going to learn how to calculate them both manually and through SPSS. It's literally just a couple clicks in SPSS. And then in our next chapter, we're going to cover the last chapter on descriptive statistics, and that'll be measures of variability. Measures of central tendency tell us how similar our data points are within our entire data set, and measures of variability tell us how kind of different our data points are within a data set. So here we go. Again, we're talking about descriptive statistics. So this entire module is focused on descriptive statistics that allow us to kind of organize and simplify the presentation of the data. So very quick ways for people to get a good idea about the general feel for the data set. Measures of central tendency, what happens is we will calculate a score, and that score now becomes kind of a representative score for the entire data set. And we have three different measures of central tendency, so they represent three different things about the data set, but they are supposed to kind of represent the entire data set. So we do have to kind of figure out which one makes the most sense to utilize under what circumstances. So that's something we'll definitely talk about. But it's really your kind of typical score. And I'm giving you kind of different characteristics of some measures of central tendency, but ultimately they're all ways in which we can describe the distribution. And because different fact patterns might influence the score, we need to be making sure we're selecting the right measure of central tendency to describe our data set based on the fact pattern that applies. And so we'll give you some general rules of thumb, and a good kind of backup plan is to look at what does the existing literature say on your particular research topic, because it's always good to kind of fall back on what does your research report, and you want to hold to that as best as possible, but you always have to look at your individual data set and what might be some reasons why you would report certain measures of central tendency. Okay, so let's talk about the three measures that we're going to study. We have the mean, and most of you are familiar with means. I'm sure many of you have calculated averages dozens of times. The mean is just the average score. We just reference it as the mean in statistics. The median represents the middle score. It's the exact middle point of the data set. So if I were to draw out the entire data set on a number line, it is the exact middle point. The mode is the most frequently occurring score. And you know, this is just a really simple definition, but there are some little nuances that can make the calculations a little bit more complicated. So just so you know that, okay? That being said, you should know that all distributions have different shapes. We talked about that a little bit in chapter 1, where we talked about how you can have a normal distribution, a symmetrical distribution. We talked about skewed distributions, where maybe all the data points pile up on one side or the other. We talked about bimodal distributions, right? So now we're talking about what does it look like when we graph it? What's the shape of that distribution? And when you actually graph it, it's depending upon the data set, it's like, where's the center point? where's the middle point, especially if it's skewed, you know? So you have to really kind of wonder, well, what measure of central tendency really helps to describe that data the most effectively? So different distributions will call for different measures of central tendency. And although we have some guidelines, ultimately it's up to the researcher, right? You determine what information you're going to report and why. And ideally, you kind of justify why you're choosing those things. And consequently, then, you know, you might have other researchers say, well, I disagree with why you reported that, or how come you didn't report that? So something to think about, okay? So when we go into the mean, we're gonna first start with the mean. It's just adding up all the scores and dividing by the total number of scores, right? So we're summing the scores and dividing by the total number of scores. And that's what we're doing mathematically. Conceptually though, I want you to think about a couple of things. First of all, every single score goes into the mean. This is the only measure of central tendency that accounts for every single score in the data set. So for some, they might say, oh, then that's the better measure of central tendency to report. Yes and no, unless your data set contains an extreme outlier. And then that also gets factored into your mean. And so it pulls that mean in the direction of the outlier. And that can be really problematic, because then we're talking about a measure of central tendency supposed to be the typical representative score. But if the mean is being pulled in a particular direction, like if we wanted to find out the median wealth for the area and we happen to have a billionaire move into our neighborhood, he's gonna make our, look, I'm even saying he, because that's in fact some of the fact patterns when we talk about wealth. Billionaires are more likely to be white males than any other racial and social identity group. So women are less likely to be billionaires, as are our Black and African American colleagues as well. So that being said, that billionaire is more likely to make it look like we're a much wealthier neighborhood than we really are. And so we have to be careful about means sometimes when there's an outlier. So that's kind of the big thing you have to watch for when you're looking at reporting a mean. If you have an outlier in your distribution, you need to take caution when you're reporting the mean, right? Know that your mean is influenced by that outlier. And so be mindful of that as a researcher, and definitely acknowledge that when you're reporting your findings. That being said, another conceptual way to think about a mean is as a balance point. So if we piled up every single data point as a Lego, right? And we put all the Legos, all the blocks on a balancing point, the mean is going to be where the fulcrum is that kind of keeps it from falling on one side or the other. And so that's a good conceptual representation, and we might draw upon that in a little bit. That being said, we're talking about arithmetic, right? Now we're getting into some formulas. I want you to take note of some of the notation here, okay? This is what we call statistical notation. When we're talking about populations, okay, remember populations, we use parameters. So going back to chapter 1, parameters are statistics that correspond to population data, and statistics are statistical or data points that correspond to samples, okay? When we are talking about parameters, we use Greek letters, okay? When we are talking about statistics, we use the regular alphabet for the English language. So here, we're talking about a mean for a population, and that is notated as mu, okay? This is the Greek name for this particular symbol, sorry, is mu. Mu equals the sum of all my x's, so I add up all my x's and I divide by n, okay? And that is going to tell me what my average is or what my mean is. Another way that you can write the formula is for the sample. Now, keep in mind that the sample and the population, the formula is exactly the same for this particular statistic. Only the notation is different, okay? Formula is the same, process is the same, doesn't matter. I just use different notation. So whenever you see a mu, you know you're talking about a population. Whenever you see the capital M, that stands for a mean that corresponds to a sample, okay? So if it's Greek, it's going to be a population parameter. If it's a regular alphabet, then it's going to be sample, okay? Both of them are the sum of all the values of X in your data set divided by the total number. Notice how this capital or this N is capitalized and this N here in this denominator is not, because this is representing a population where we would capitalize, and this is representing a sample where we would not. Okay, so just the little tricks in your notation, and each chapter will learn a little bit more notation. So you're kind of learning a couple of different languages. You're learning terminology, which, hey, it's okay to write out some note cards and actually do some vocab memorization. But then you're also now learning the language of the notation and how do we mathematically notate what we're doing, our formulas. You don't have to memorize your formulas, but developing cheat sheets is really helpful. And I also developed some cheat sheets for you, and those are good resources and tools, but it's always more helpful if you develop your own cheat sheets. That's always more effective. Research is very clear on that, okay? Okay, so let's go on and let's talk about another kind of mean. A weighted mean is basically when you have two groups and you want to find the combined mean between those two groups. And some people accidentally, or they just think, oh, well, it's just the average of those two means. That is incorrect, because remember, every score factors into that mean. What if one group has 100 people and the other group only has 50? Which mean do you think is going to be more powerful and have more weight in the overall mean? It's going to be the larger sample, right? And so we have to keep that in mind. And if you think of it as that fulcrum, that kind of balancing point, you definitely can realize that the sample with more people is going to have more weight on the overall mean. So we can't just average two means together of two groups in order to get a weighted mean. We have to look at their representative populations or sizes that are going to contribute to that overall mean. So what we really need to do is we need to kind of look at our formulas, and we need to say, okay, we have to account for the separate sample sizes, right? So our weighted mean formula is we are going to do the sum of all, when we do the subscript right here, that's saying for group 1. So the X1 represents all of the raw scores for group 1, and the N1 is the total number of people in group 1. And here we have X subscript 2, so that's all of the raw scores for the second group. And this N2 is going to be the total number of participants in the second group. So what we do is we sum up all of the scores for group 1 plus all of the scores for group 2. We do that first, and then we add the sample size for group 1 and the sample size of group 2, and we're going to do our division, right? And our division is ultimately going to result in our overall mean. And so we have to remember the mean's not the halfway point, that's the median. The mean is actually that balancing point. So sample size matters. Now, it's really important to recognize we use weighted mean a lot in academia. Some of you may have had classes where exams count for a huge portion of your grade, or maybe a project or, you know, a final counts for a huge portion of your grade. So this is another formula that you can use right here that will help you if you have a class that has weighted means. So you're going to look at your total of your score times that weight or that percentage of your overall score, and you divide that by the overall weight overall. So in other words, 86 times the weight is going to be 0.5. And our overall, we're looking at what our overall total points are. That's going to be about 43 if this is out of a total 100. So we're going to get effectively 43% is going to come from what we scored, okay? And then if you have a 96 on your midterm, that's 15% of your grade. Ultimately, it's going to account for 14.4%. If you got 100%, it would count for 15, right? But it's not. It's only 96% of the 15%, 82 of the 20%, 98 of the 10%. And so overall, this person's scores are going to result in a little bit above, well, about a B plus in this class. So just a little under an A, okay? Well, I kind of use weighted means, but it's all based on points. So in our class, we just look at the total number of points, like you're just earning a bucket of points, and what percentage of points do you get in the end? That's ultimately how we do it. Okay, so when we talk about computing a regular mean from a frequency table, just like we talked about in chapter 1, you have to pay attention to the fact that we have to recognize there's not just one 9 here, there's 2 9s here, right? Every single score has to be counted in that calculation. So remember how we did that sum of x equals essentially the sum of f of x, right? So you have to pay attention to that. And so what you're gonna do is you're going to follow that same pattern we gave you where you have your scores, your frequency, and you create a column that says f of x. And then we have a sum of f of x of now that's going to be the actual sum of all the scores. Sum of x is effectively the sum of f of x when you're using a frequency table. And then you're going to divide by the sum of the frequency, because that tells us the total number of participants. Remember, that was a way you could check yourself. Total all your frequencies, and they should equal your sample size. So we're essentially saying the total of all x's divided by our sample size. So a really quick kind of rework of the formula in order to let you calculate your mean from a frequency table. So I'm going to give you an opportunity to practice. I want you to go ahead and just pause and then write it out. Remember, working through these examples is really important because it's like driving. It's giving you that practice, that behind the wheel time, so that you can learn and practice these skills, and it'll stick with you a little bit, okay? So just pause me, work through the motions, and when you're ready, go ahead and click play. Okay, perfect. So let's go through these together, okay? First of all, we're gonna find the mean for the following scores. And we have a total sample size of 5, and those 5 scores equal 1, 8, 7, 5, and 9. So in order to calculate the mean, we're gonna have to add all those up. So that's 15 plus 5 is 20, plus another 10 is 30, divided by 5 equals 6. So our mean is 6. In this number 2, we have 6 scores, and the mean is 8. Now remember, when we're just like in algebra, if we know, if our formula has 3 figures and we know 2 of those, we can solve for the others, okay? So in this case, we know the total number of scores, which is the denominator for our formula. We know the mean is 8, so it's asking us what's the value of sum of x. We have to solve for that now, okay? So if we plug it into the regular mean formula where mean equals the sum of x divided by n, then what we have to say is, okay, what can be divided by 6 to equal 8? And that's 48, okay? So know that in this chapter, you're not just solving mean. Sometimes it'll make you use the mean formula to solve for some of the other variables, okay? So you have to be able to rework the formula in order to provide whatever data is in question, okay? Okay, so number 3, one sample has n equals 5 scores with a mean of 4. So again, I have my sample size and my mean, but I don't have my sum of x, right? A second sample has 3 scores and a mean of 10. And so if the two samples are combined, what is the mean for the combined sample? Now we're talking about a weighted mean, right? Because we have 2 or more samples. And when looking at this, we can say, okay, this has 5 scores, this has 10 scores. So our mean should be closer to our mean is going to be more heavily weighted by the larger sample size. So I'm looking at the wrong thing. This isn't 10 people, sorry. This is our sample size, n equals 5, and here it's n equals 3. So this mean will be more heavily weighted than this mean, because it's only 3. So we would expect then that our overall mean would be closer to the mean for the larger sample than the mean for the smaller sample, okay? Now we plug in our formula. Sum of x for 1 equals the sum of x for 2. Notice I wasn't given the sum of x. So my first step is to solve for the sum of x, okay? So that's what I'm doing here. I'm solving for my sum of x. And then I am dividing by my sample size of 5 and 3, right? And I am able to now, I'm now able to get my combined mean. So ultimately, I am figuring out this answer is 20 plus 30 divided by combining my sample sizes is 8 equals 6.25. So my mean, my overall mean for 2 groups where it's the weighted mean that were originally 4 and 10, my weighted mean is now 6.25, okay? And if I add these up, 14 divided by 2 is 7. Notice that 7 is 6.25, which is our overall mean, is not the same as just combining the 2 means and dividing by 2, okay? It's going to be lower than that because it's more heavily influenced by the group with the larger sample size. These sample sizes aren't that big of a deal. They're not that far apart. So the mean's not hugely different than what it would otherwise be. But if the samples were more extreme in sizes, then it would have a bigger impact, okay? Number 4, a sample of n equals 6 scores has a mean of 40, okay? Our new score, one new score is added to the sample and the new mean is found to be 35, okay? So first I have to look at the overall score. I need to figure out what my sum of x is. And then I'm saying a new score was added and now my mean's going lower. So what can I conclude then about that extra score? It also had to have been less than 40, right? Because it's pulling my mean down. So it had to have been pulling my mean backward. I may have slipped a slide. So I may have skipped a slide. So I want to go back in just a second and check that. And finally, number 5, I want to find the values of n, right? How many participants do I have? Remember, n is just equal to the total frequency. So I can just add those up, 3, 6, 11, 12, right? Total frequency. And then my sum of x, I'm going to do that f of x trick, add those up, and that's going to be 33. And the mean for the sample that's summarized below. So I get my frequency table, and I'm going to now calculate my mean, and I need all of the components that are factored into my mean formula, okay? So now my mean equals my sum of x, 33, divided by my total n, which is a total frequency, equals 2.75 for this particular data set. Make sense? Okay, I just want to skip back for just a second and see if I skipped a slide. I didn't. So interestingly enough, I'm just asking you to use logic, but I will go over some kind of general things about the mean so that you can also kind of know when we talk about it must be greater than 40. If we add a mean, what happens? Or if we add a score, what happens? If we take a score away, a score, what happens? So here's some things. Characteristics of the mean. Every score is part of your mean calculation. These slides really should be flip-flopped, okay? Changing the value of any score is going to automatically change the mean. Why? Because it changes the sum of x. And the sum of x is a critical component of the formula for the mean, right? So if it changes the sum of x, it's going to change the mean. So any score that's changed in a data set is going to change the mean. So let's say you do all your calculations and you're like, oh shit, I input participant number 29 wrong. That's not their score. Well, if I change that, it's going to trickle and change other things too, including the mean, okay? Additionally, let's say, oh my gosh, we forgot to enter data for this other person. I just found their surveys. Let's add them into the study. So if I add a score now to my data set, it's going to change the mean. The only time it's not going to change the mean is if that score is exactly the same as the existing mean, okay? So if you add a score or you remove a score, it changes the mean unless the score is exactly the same as the mean, okay? Additionally, if you add a constant to every score, so let's say I want to bump every score by 5 points, it's going to now bump the mean by 5 points. So that's something I do, like if I want to adjust scores are low on a quiz or an exam, I might bump them all, right? It's going to bump the mean. If I subtract a score, it's gonna bump down the mean, okay? Same thing if I'm multiplying or dividing. A constant means I'm doing it to every single score in the data set. If I'm multiplying every score by 2, then what happens is it's going to also multiply the mean by 2. If I divide every score by 2, it's going to divide the mean by 2. So whatever constant I apply to every single data point in the data set, it's going to affect the mean the same way, okay? Okay, so here's a couple other practice problems regarding the mean. So again, go ahead and hit pause and then work through those answers. And then start me when you're done. Okay, so assuming you're ready now, adding a new score to a distribution always changes the mean. Always. No, it only changes the mean if the new score is not exactly equal to the mean. So it's really important. That would be false. Changing the value of a score in a distribution, changing the value of the score is going to change the mean. Yes, because it changes the sum of scores, the sum of x, which then also changes the mean. So a population has a mean of mu equals 40. If 5 points were added to every single score, so we added 5 points to every score, what happens to the value of the mean? It's going to increase by 5 points because we add 5 points to it too. So our new mean would be 40. If we multiplied every score by 3, we also have to multiply our mean by 3. So your new mean would be 120. And then finally, a sample of n equals 4 scores, so we have a sample of 4, has a mean of 9, okay? So I know my sample size and I know my mean. I don't know my sum of scores, right? If one person with a score of X equal 3 is removed from the sample, what is the value of the new sample? First thing I have to do is solve for the sum of X. Then I'm going to reduce that by 3. So that's what you see happening here. What is the sum of X? What number can be divided by 4 to equal 9? 36. Now I'm going to reduce that 36 by 3 because I'm removing a score, a 3 score. That's going to bring my new sum of scores to 33. And I'm now, instead of having 4 scores, I only have 3 scores. So I'm going to take that 33 divided by 3, and my new mean will be 11. Okay. So some questions might require you to kind of think a little bit and say, what do I need to do first, and then next, and then next. Math is really about logic. It's about figuring out how to solve problems. I know a lot of people say, oh, I hate this math crap. It teaches you critical thinking. It teaches you logical reasoning. And those are always wonderful skills to have, and those are always skills employers are looking for, okay? So know that it's building those skills in you. So let's move on and let's talk about median. Remember I said earlier, the median is the middle score, okay? So if we were to line them all up, it's the exact midpoint of the score. We don't really have any kind of notation. Sometimes you might see it abbreviated a little bit, just MDN, but there is not any statistical notation, so you don't have that language to learn. We don't have any changes in how we define it or notate it, whether we're talking about a population or a sample. Doesn't matter, it's always referenced as a median. And we typically, in order to figure out the median, we go from smallest to largest. That usually, that midway point becomes our median. So it is the point at which exactly 50% of the scores fall on the left and 50% of the scores fall on the right. Now that can be tricky when there's an even number of scores. So we'll talk about a precise median, and that requires the calculation where we have to cut up that midpoint into fractional pieces to get the precise midpoint, okay? So our scores are effectively divided. It's like a pie. I'm dividing it into equal sides where you get, your half is exactly equal to my half. It's like a divorce pie where you get 50% and I get 50%, unless you're my ex and then you're trying to screw me out of my 50%. Okay, so let's talk a little bit about how we figure out the median. When you have an odd number of scores, it's fairly easy, right? It's that middle score, boom, that's it, okay? So when there's an odd number of scores, boom, the middle point, here we go. We have 5 scores, the middle score is a 3, it's in the middle, you tag your median's 8, okay? But now notice here you have 6 scores, not quite as easy. Okay, so what we do when we're talking about an even number of scores is we take the 2 middle points and we divide by 2 for 4.5. That's kind of a general median, but it's not the precise median. So we like to complicate things just a little bit, and we need to think about precise medians when we're talking about continuous variables. Because remember, continuous variables can be broken down into incremental parts, right? And so what we want to look at is the fractional pieces of that score that need to be added in for the median in order to get a precise median. So precise medians only apply to continuous variables. And if you don't entirely understand that, this is okay, because really the only time we're going to talk about precise medians is, frankly, in this frickin' chapter, okay? In reality, SPSS calculates all this shit for us. We don't have to worry about it. So I don't want you to stress out too much. I want you to try to understand it. I want you to take really good notes, read it a couple times, try to calculate it, do your best. But if it's something you just can't wrap your head around, don't stress, let it go. If you have to miss a couple problems on a quiz or an exam, it's not gonna hurt you. I have extra credit built in to cushion you. Don't worry about it, okay? don't lose any sleep over it. There is more important shit in the world to be worrying about than this precise median, okay? So let me just say that. Now, let me go back to teaching you about precise median. It's fractional. We're talking about a continuous variable that's fractional, effectively. It's our Legos. We can break it down into smaller and smaller pieces. And you know, you have the big old giant Legos, and they can be broken down into little itty bitty tiny Legos, okay? So we want to figure out is how many itty bitty Legos make up a bigger Lego, and how many precisely do we need to be that midpoint. So if I were to actually measure the total amount of area of Lego space that you have, it would be exactly the equal to what middle point of what you have on both sides, okay? So we have to divide things into fractional scores. Conceptually speaking, we're really just talking about how much does it take to get to 50%, okay? And so here's a little bit of challenge. I personally need to use visuals for this, so I'll lead you to this in a second. We have to take into consideration the real limits that we talked about before. Remember, that real limit is that those exact boundaries, the halfway point between, if I'm talking about a number 50, the previous number, so it's the halfway point between the previous number and 50, and it's the halfway point between 50 and the next number, okay? So it's those boundaries, that upper limit and that lower limit, or lower limit and upper limit, okay? So you have to know your real limits come into play when we're calculating precise medians, okay? When we're calculating imprecise medians, doesn't matter. But when you're calculating precise medians, those upper limits matter, okay? So I want you to look at this right here, okay? You have a sample, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points. So it's an even number of data points. It's not clear and obvious what the median is. So we figure, okay, well, it should be somewhere around 6. So both of those right here in the middle are 3 and 3. It's not just 3, because remember, it's like making sure that 50% of the Lego mass is on one side and 50% of the other. It's the exact point at which there's 50-50. It's not as simple as that. What we need to do is we kind of need to look at, well, hold on, there's 4 3s, right? There's also, when I look at, oh my gosh, there's 2 2s and 1 1s, but then there's 3 4s and 2 5s. It's challenging, right? So I'm gonna have to say, okay, it's gonna be 3. So I need to know what my median is, or excuse me, not what my median is, what my limits are for 3, okay? So what is my upper limit and what is my lower limit? And I start with the lower limit of the number before my 3, okay? So I'm gonna, remember, your lower limit is based on the number that preceded your number. So I'm at a 3. I need to look at what is the upper limit for the number preceding and the lower limit for 3. That's going to be my 2.5, okay? And then I need to say, okay, I need to essentially get a total of 6 scores on either side, right? So I say, okay, I already have my 1, 2, 3, 4, 5. How much of this 3, assuming those boundaries, do I need? How much of this 3 do I need to get 50% on this side and 50% on this side? And what I end up doing is I end up having to take a percentage of these 3s. I'm going to advance to the next slide because it's easier for me to think about it visually than it is for me to think about it numerically, okay? This is where, remember I said that modified histogram is helpful? because in a modified histogram, I get one single block for every data point. So here I know I have 4 4s. I have 1 1, 1 2, 1 3, 4 4s, and 1 6. Where's my median? I have a 1, a 2, a 3, a 1, 2, 3, 4 4s, 1, 2, 3, 4, and a 6. So I have 2, 4, 6, 8 scores, right? Again, I have an even number of scores. I need a precise median. What I do now is I'm looking at 8. It's going to be somewhere around these 4s. What percentage of the 4s do I need in order to get a precise median? I start by going to the score below. And I say, okay, what is my upper limit for the score below, or my lower limit for 4? That's going to be 3.5, okay? So this actually kind of starts at 3.5. And then I say, okay, what percentage of the entire 4 column do I need? Because these are stacked up, okay? What percentage of those do I need in order to have a total of 4 blocks on this side and 4 blocks on this side? Well, I already have 3 blocks here. I really just need 1 more block. Since I have 4 4s, 1 more block would be 25%, because I just need 25% of all 4 blocks is going to give me a whole block, okay? So it's essentially taking a big Lego and breaking it down into 4 little Legos that when you put them all together, they're the same size as the big Lego, okay? So I just need to know what percentage of the big Lego do I need to have 4 small Legos over here and 4 small Legos over here. And I take my 3.5, because that would be my upper limit for 3 and my lower limit for 4. And then I add my 0.25, because I just need 25% of this big Lego in order to get 4 small Legos on this side. So it's going to be 3.5 plus my 0.25 equals 3.75 is my precise median. Does that make sense? I always have to draw out a chart in order for it to make sense for me. There is no special formula that we follow, because it's a conceptual thing. And as I mentioned, like, if this doesn't make sense and it frustrates you, then know it'll never come up again. And know that we'll just rely on whatever median SPSS gives us, okay? But I will let you practice a little bit. I will let you try to prepare for the homework a little bit. But again, if the precise median is just like ripping your hair out, don't stress. If you can draw out visuals, great. If you go on YouTube and find another video, or you have some knowledge from some calculus class that might be helpful, share that with us. Let us know. Let's upload some resources in the class that might be helpful. I do post a video that does give you a little bit of help, but you know, you also let me know if I can add more, okay? Okay, so go ahead and hit pause, do your calculations for your practice, and then when you're ready, hit start. Okay, so assuming you have gone on and moved forward, when we're talking about the median for each of the following scores, for A, it's pretty simple, right? You have 7 scores, 2, 4, 6, 7, and so our middle number is going to be our median. And then here, we're not looking for precise median, so all we're going to have to do now for this number for B, that includes just averaging those 2 middle scores, so that's 11.5. It's when we get to precise median that it's more complicated. So if you have a score of 52 on an 80-point exam, then you definitely scored above the median. Is this true or false? We have no clue. We don't have enough information, right? So it's false, because it's saying you definitely scored above the median. We don't know, because we have to know what the other scores were in order for us to determine if we're the midpoint score, okay? Number 3, the following is a distribution of measurements for a continuous variable. Remember, precise medians apply to continuous variables. Find the precise median that divides the distribution exactly in half, taking into account those upper and lower limits. So when we look at these scores, we have 2, 4, 6, 8, 10. So we're looking at the point at which we have 5 on one side and 5 on the other. Little blocks, not big blocks, little blocks. So we're battling with these 4s. How much of the big block of 4s do we need in order to get 5 on one side and 5 on the other? We're going to start with the in-between number, right? What is that upper limit for 3 and that lower limit for 4? It's going to be 3.5. I just want 5 scores. I already have 1, 2, 3, 4. I just need 1 more. So I just need one of these 4s, one of these 4s. So if I stack them all, right, I just need 20% of that big column of 4s. And that's going to be 3.5 plus 0.2, which is 20%, is 3.7, because I have 5 4s. I just need 20% of them. In order to create one block, one little Lego block, I just need 20% of that big column of 4s. Make sense? Draw it out visually, see if that helps you. Okay? I'm going to move on to mode. Mode is our most frequently occurring score. So we don't have any symbol, there's no notation, you just write it out mode. There isn't even an abbreviation, you just write it out at mode. We don't really differentiate between a population mode and a sample mode. They're both the same. But it is looking at the most frequently occurring score. So what score has the highest frequency? That's your mode. It's as simple as that. However, can be a little complicated because maybe some scores are both, they have the same frequency, right? So there are times when you might have a bimodal distribution, bi meaning 2. I have 2 scores that have the highest frequency. I could have a multimodal where 3 or more scores are the highest frequency. So I have 3 or more modes, right? Or I could have things that are basically unimodal. They all have the same frequency. So when I'm trying to calculate mode, I gotta look at my frequency data, okay? So hit pause and see if you can go through these and answer them. And when you're ready, go ahead and hit play and we'll move forward. Okay, so here we go. When we're talking about mode, we're gonna look at during the month of October, an instructor recorded the number of absences for each student in a class. N equals 20, so I have a total number of 20, and I got the following distribution, okay? What is my mode for this distribution? We can clearly see it's 3, right? 3 is your mode, because that's what I had the most frequently, that was the most frequently occurring score. Now, some people might say, oh, 7's your mode. No, 7's your frequency. Your mode is the actual raw data score, right, that occurs the most frequently. It's not the frequency score. It's the raw score that occurs most often in your data point, okay? So it's gonna be 3, your mode is 3. So now it's saying, using the mean, what's the average number of absences for the class? So whenever we hear averages, we're gonna use mean, okay? Same thing. So because it's a frequency table, we're gonna do our f of x, and we're gonna divide that by 20. And we're gonna see for this data set, our mean number of absences is 2.35. With the median, I'm going to say, what's the average number of absences? Remember, measures of central tendency kind of tell you what's the typical score, right? With the mean, it's going to be the exact average. With the median, it's really the midpoint. But I'm saying, hey, tell me kind of what's the usual amount of absences I should expect for this class. I can give you a mean, a median, or a mode, right? And I can say, oh, okay, well, the average absences are 2.35. and that was determined by looking at all the absences for every point in the data set. And when I add those all up and divide by my total number of students, on average, students are absent 2.35 times. When I look at the median, that's the midpoint. The middle point is the exact point at which 50% of students are on one side and 50% of students on the other. And that number is 2.5, so a little bit higher than the average because I had some individuals that had absolutely no absences, which kind of pulled down my average a little bit. So my median, not true outliers, but still enough that pulled down my median a little bit. So 2.5 is the median, the middle amount or midpoint of averages that I had. And then when I'm looking at my most frequently occurring absences, 3. So most people are absent about 3 times. Some people are absent never, or as little as 1 to 2 times, which brings my average down to 2.35. Makes sense? Okay. You have to keep that in mind when you're looking at a data set. What score makes the most sense? What do I want to report? I need to understand what is contributing to that score, what that score means, based on my data set, what's the most appropriate to be describing, what is causing or influencing my outcomes. So you need to talk about those things, okay? And you're going to do that in your SPSS assignments. So when we talk about selecting your measure of central tendency, we really do prefer to use means because every single score is taken into that calculation. However, we have to keep in mind that means can be skewed based on any outliers. So when you have an outlier, it could be problematic. We also are going to use means. You're going to find out for almost all of the inferential techniques that we utilize. Means are going to be really, really powerful. Means and frequencies. Frequencies are going to be used for chi-squares. We're going to use frequencies. But all the other inferential techniques, the parametric techniques, we're going to use your means. And means are factored into your variance and your standard deviation, which are in fact the descriptive stats that are used for your inferential calculations, okay? But remember, we can't always calculate a mean. Let's say that I was doing a rat maze, a study looking at learning efficiency with some sort of reward. So I offer them cheese to finish a new maze, and some rats like never figure out the maze, even with the cheese. Well, they don't have a score. So I can't calculate a mean all the time. So in that case, it wouldn't be appropriate for me to report a mean. The median is really great when you have some extreme scores. When you have those outliers that are throwing off your mean, it's probably more appropriate to report your middle number, right? Because that mean is skewed a little bit. And then you do know your median isn't as affected by those extreme scores at all. We're looking at that midpoint, okay? The point at which 50% of scores on either side. So they can also be effective even when you have a score. We know what side it is on. If the rat never completed it, we know what side it is on, even if we don't have an exact score. So a median could be utilized in those circumstances when we just can't calculate a mean. And then additionally, when you have like an open-ended distribution, like you scored 5 or more, or something like that, then we can utilize means or medians again. So, and also when you're talking about ordinal data, so number of people in the race, right? We see how they ranked. The median score or middle score tends to be used most commonly with ordinal data. And then the mode, when we're talking about nominal data and it's just categorical, right? They're just different in name only. The mode is the only way to report it. We don't calculate means. That's probably not appropriate. So we would report the mode saying, hey, this is the category, like if strawberry vanilla chocolate ice cream, this is the most popular ice cream flavor. So we use modes always when we are reporting nominal data. The variables are discrete, so they're not continuous, they can't be broken down. And And also, modes kind of give us a really good picture of what that shape looks like. Where's the data falling? If we know the range and the mode, we get a really good idea just right off the top of what the shape of the distribution is, okay? So here's a good chart that helps you kind of know when you might report one chart or the other. So come back to this particular PowerPoint, and particularly this last section, when you're doing your SPSS homework. If you have any questions or you're struggling and you're saying, what do I report? Because I'm having you do narratives. I'm having you describe your data set. You have to, as a researcher, describe it to me. What does it look like? Report your measures of central tendency. And you have to know, well, which one would be most appropriate to report? You're going to report them all, but you're going to talk about don't just regurgitate data to me. Kind of communicate what your understanding about the data. What does it all mean? Why would we report one measure of central tendency over another? What factors are contributing to the outcome for that particular measure of central tendency that may make it more appropriate or less appropriate to report in the research, okay? So do that and use these as resources. And also, when you are talking about the research and the literature and how is this published in empirical studies, APA guidelines, we abbreviate a mean with capital M. We most often see means reported and standard deviations reported in our studies, in our empirical articles. When you do see the median reported, it's often abbreviated MDN. That's most often in tables or some sort of graphic. Otherwise, when we're writing it out in the narrative portion, like the results section, we usually write out MEDIAN, so we spell it out. And so you might see it in a particular study as the median number of errors for the treatment group was 8.5 compared to a median of 13 for the control group. Up above is an example where you would say the treatment group showed fewer errors. In parentheses, we're saying on average 2.56 for the treatment group. Fewer errors on the task than the control group, and the control group had 11.76. So whatever the treatment it was reducing the number of errors. Okay, you see that the treatment group had significantly lower number of errors than the control group. Okay, and then modes, we just spell it out, MODE. Okay, okay. So here's some tables that might be appropriate. And how you might see our measures of central tendency represented in graphical or tabular form in our papers. And so this is very common where you're going to see means quite often reported in our tables, often with standard deviation, but we're not there yet. And then here you are actually having they're reporting the mean food consumption. So your y-axis actually represents the average food consumption for no drug dosage, 1 drug dose, 2 drug doses, 3, 4. And then over here, you're seeing a categorical variable, and you're looking at the median house based on these different categories. So in the Northeast, the median house cost is about $225,000. In the South, about $150,000. Notice the West is significantly higher. You have to have a really good education and a really good job, and often a 2-income household to buy a house in California. And forget it if you're trying to buy a house in Santa Barbara or even San Francisco, right? Okay, so let's talk a little bit about the shape of distribution, and then we're going to wrap up this chapter. When you talk about symmetrical, remember you can fold those in half and they're exactly the same on one side and the other. Symmetrical distributions with only one mode end up having the mode right down the middle, right down the center. And so in that case, that actually is going to be a normal distribution where the mean, the median, and the mode all equal one another, okay? But if you have a bimodal distribution, remember like our drawing from our past lecture, when you fold it in half, they're still gonna be symmetrical, right? They're gonna be mirror images of one another, but you have 2 different modes. So it's not a normal distribution. Remember, All normal distributions are symmetrical, but not all symmetrical distributions are normal. A rectangular distribution might just have no mode because they all have the same. There's no one that's more frequently occurring than the other. When you have a positively skewed, remember the numbers are going to pile up on the left side and it's going to point toward the positive end. The tail is going to point to the positive end of the number line. Then you're going to have the mode, and then you're going to have the mean, and then you're going to have the median. But on a negatively skewed, you're going to have the mode, and then the mean, and then the median. So it's left to right when it is positively skewed, and it's right to left when it is negatively skewed. So here's what that looks like. Here's when you have a normal distribution. The mean, median, and mode are all equal to one another, right smack in the middle of the distribution. This is a bimodal distribution where you have the modes on the outsides and the mean and the median in the middle. So when you fold it in half, those modes kind of mirror one another, okay? Here you have no mode, just a big fat rectangle, right? Just flat, nothing's higher than the other. They're all the same. That's just a no mode. Then when you have a positively skewed distribution, you're going to have your mode is always your high point because that's, remember, the most frequently occurring, and we use frequency on our y axis. And so that's the most frequently occurring. And then it goes mode, median, and mean. Notice your median's always in the middle, okay? And notice over here, your tail's over here, which means you have a score over here. So that's pulling the average toward that end of the number line, okay? So it's pulling your mean down when it is positively, or it's pulling, excuse me, pulling your mean up when it is positively skewed. Okay, it's pulling it higher, which means your mean is always going to be higher than your mode. Here, on a negative skew, it's the opposite. You have an outlier over here toward the negative line. So it's pulling your mean down, which means that your mean is going to be lower than your mode. So on a positive skewed, your mean's always going to be higher than the mode, and the median's always going to be in the middle of the two. In a negatively skewed, your mean is going to be lower than your mode, and your median's always going to be in the middle. So again, keep this visual handy because this is a great cheat sheet for you. But also just think, if you're logically understanding what a median is, what a mean is, what a mode is, then it also translates into understanding how that affects what the distribution looks like. Something you need to consider when you are talking about describing your distribution for your SPSS homework assignment. Okay, so let's practice a little bit. Go ahead and hit pause, read through the questions, work through those answers. Okay, so assuming you're ready to go. The mean uses all scores in a distribution, so it probably is the best measure to use in a skewed distribution. Nope, that would be false, because a skewed distribution, sorry, my bunny's chewing on stuff, I gotta get her. A skewed distribution is pulling that mean down, right? So when it's skewed, you don't want to use the mean. It's not the best representation of typical scores, okay? The mean and the median have the same value, so the distribution is symmetrical, okay? True. If the mean and median equal one another, it's a symmetrical distribution, okay? And then number 3, a distribution of scores shows a mean of 31 and a median of 43. So the median's always in the middle of the mean and the mode. So what's happening? It's pulling the mean lower, right? So now the mean's here, the mode's higher, or excuse me, the median's higher, and our mode would be higher. So it's going to be a negatively skewed distribution. Whenever the mean is lower than the median, it's going to be negatively skewed. Whenever the mean is higher than the median, it's going to be positively skewed. My bunny's being a little bit, oh, she stole a candy. Hold on, I gotta get her. What are you doing? What are you doing? So my bunny is a bit of a chocolate addict, and she stole a candy, and so I had to get it from her because Bunnies aren't supposed to, I don't think they're supposed to have chocolate, but I don't need her keeping me up all night either. Okay, so that's it. I hope that was helpful for you. I'm going to stop sharing. I hope that was helpful for you, and work through your homework assignments. Let me know if there's any problems, and I'll see you in chapter 4.